So that sheet I've just given you is, I'll show the camera, technology. So I've just given you this sheet. It's got three bits of paper. They're all basically the same parts, but with a little bit extra on each one that's not covered in. So they've all got the unique dimensions in. But the first one you've got on the first side is the one we're going to start with. So more of that as we get going. So dimensional analysis. So I've written this verse up out of the Bible, Genesis 1, verse 1, first verse in the Bible. Okay, because it says in the beginning, so you've got time, God made the heavens, which is L for space, and then the earth, which is your mass. Okay, as I mentioned earlier, that comes out of the Latin massa, meaning earth or physical being. So, and I just thought that was an interesting verse, how it applies. I find these things fascinating, so I just thought I'd put it on there. But you don't worry about it, you don't have to get heavy on it. So it's got 4 uses. It'll all come together as we go through it, but it's got 4 main uses. To check formula, which is what we'll be doing. To derive relationships between physical quantities. Well, what that means in English is we can make formulas, we can derive formulas, which is the other thing we'll be doing. To convert from one unit to another, and I have done a bit of that, but I couldn't tell you how to do it now because it's not something you ever need, because that's what Google does for you. You just put it in one unit and it'll give it in another one if you use a conversion. So what it means by that, for example, changing, say, kilometres into metres or centimetres, that kind of thing. So it's not really something you really need to use. And this last one is pretty important, but we won't be doing this either. This is to find the units of constants. So this is, for example, what Isaac Newton would have used. You know, when he found G, is a universal constant G. It's got units. Some constants have units and some constants don't. And this is a G has constants. Units are constant for that constant. So, and you can look them up and find them. So you could use this method to find them, which is probably what Isaac Newton did. These first 2 are the ones we're going to concentrate on. So what you've got, you're familiar with SI units. So these 3, for example, metre for in kilograms for how heavy something is, how much mass it's got actually, because the heaviness only comes from the pull of gravity on it. Length for distance, L for distance, so that being units of metres generally, normally, most commonly. And then T for time. We usually use a small case T, don't we? But in dimensional analysis it's an uppercase T. And they're usually put in square brackets. So you'll notice on your formula that sheet that I'll give you, they're not, except for the last one. But generally speaking, they're put into square brackets. And as we go through it, this will all make more sense, so don't worry about it. But you'll see from looking at these sheets, everything that you've got can be defined in terms of these 3 things. So we talk about base units, the 7 of them in, I think. We talk about those, and actually there's only 3 really, and everything else can be defined in terms of that. So for example, if you've got length is L, and then you've got, if you look at say velocity, it's distance, so it's in metres per square, metres per second, sorry, or like that if you prefer. Okay, so that would end up being, in dimensional analysis, that would be L, and then it would be displacement as second, sorry, as displacement to the -1 because it's on the lower, it's a division. If you remember your laws of indices. I'll just say something about displacement, by the way. Do you know the difference between displacement, length, and distance? There's a difference actually in the SI units. So the best way to explain it is if I go out this door, go out onto the balcony, go down the steps, come back up the other steps, come back in here. Say I stop here, for example. I've done quite a long distance, but I've only ended up 1 metre from where I started. So your displacement is where you end up from where you started, how far you displaced. Okay, so you do a lot of distance and still not do a lot of displacement. So you can be tired and you feel like you've not got anywhere. It's like life really. Okay. So that's the difference. So that's the application. So you'll see on here as you look through it, you can see that acceleration is LT minus 2 because it's meters per second squared. Another common force is an M, an L and a T minus 2. So you've always thought of force as being in newtons and etc. Meters per mass times acceleration, these kind of things, but it's all tied in, they're all tied together. And you start to see this, you start to see these patterns occurring. So these three things keep coming back. So it goes all the way, energy, power, density, etc., etc. They've all got these units. And what happens with some of them as well is the units might be long to start with, but they start to cancel out. So you might have a T on the top of your formula, and a divider of a T, so minus 1 in other words, so they cancel out. So your dimensions might end up a little bit simpler than your first thing. Okay. So another thing to bear in mind is that length. If you've got area, so you've got area, you've got L times L.
L squared.
So yeah, so that becomes L squared. Okay. And if you've got volume, obviously, volume ends up being L to the 3. So it's still the same dimension, but there's 3 of them. Now, interestingly, if you look at, let me find where I put it on my notes. If you take an example, there's a thing called homogeneous, or I'm not very good at saying this, I can't say it, homogeneity, forget it, I can't say it. But it's got to be homogeneous, so a formula's got to be homogeneous, so the left hand side's got to equal the right hand side. And it's quite interesting, if you look at the formula for volume, for example, volume of, would that be a sphere? This one, for example, pi r squared h. It's not obviously, it can't be, that must be cylinder. If you look at this, it's got, here you've got, a radius is a length, so that's an L. And there's 2 of them, and the height is another
length as well.
Another length, yeah. So you've got another L. So you've got basically L to the 3. Okay, which is what volume is. Pi, incidentally, is a constant. This is a constant without dimensions. So they don't actually count in the calculations. Okay, that if we were deriving the formula, that would just be we'd just use the term K, and you may have to work that out by other means. Okay, as I did with pi. So you might have to do experiments to find out what K is. Quite often things do end up being pi, or 2 pi. So any numbers out front, any constants, any coefficients don't count in the process. They're obviously important in an equation, but they don't count in the working out of the formula. Okay, so pi wouldn't, if I were working this out from what as we're going to do with some of the examples, I would we'd have to work this out by other means. We just have a letter K there for constant, some unknown. That unknown ends up being pi when we do further investigations. We'll see some of that as we do some examples. This will definitely fall into place better as we do examples. Okay. So so that aspect of the balancing is this first one. This is what we use. So anytime any scientist came up with a new formula, like Albert Einstein, for example, Isaac Newton, they have to check that the left and right hand side of the formula is balanced. If they don't balance, then it's incorrect. Yeah, it's wrong, so it's rejected. So that's the first thing they need to do, is check it balances. There may be some constant in there to allow it to cater for, and that might explain something, maybe, a mistake maybe. So let's have a look at an example. Let's go with, talking about Albert Einstein, let's start with that one. So Albert Einstein said, leave them up for now. Albert Einstein said this, mc squared. You're all familiar with that. It's probably his most famous formula. So he derived that, and it was quite a revelation when he did, surprisingly, maybe. These things that people discover, they're always obvious, aren't they, afterwards, until you discover them. Maybe not general relativity and special relativity, they're a bit not obvious, I guess. But a lot of other things can be fairly obvious. Anyway, so M is for mass, C is for speed of light. Okay.
So length.
So 2.998 times 10 to the 8. Okay. So the units for that would be, also, well, before we get to that, we've also got other formulas for E. There's a lot of formulas for E for energy. For example, we've got another E formula is half mv squared. You can see the pattern there actually. Another one is E equals mgh. So if you raise something up to a height of a certain mass, gravity is pulling on it, and the height, the amount of height you raise it to decides what amount of energy it's taken. So that's your potential energy. If you release it, you get kinetic energy. This one comes into play. So you've probably seen those before. So if I take a couple of these, as per my example here, let's use half mv squared to start with. So this one, we've got energy. So if I look that up, energy on my sheet I gave you, we've got mLT minus 2. So m is the mass, and these two both relate to the speed of light, so it's a velocity. So velocity, velocity. Yeah. I'm confusing myself here. Why have I got minus 2 in there? That should be 2, sorry. That's why I got confused. Okay. Velocity squared. So velocity, that's why it's minus 2. Sorry. Because velocity is this. Would be LT minus 1, isn't it? Okay. But because it's squared, multiply it in, which is going to give me, would give me 2 and 2 there. Okay, so let me just clarify my...
What have you done there, Kevin?
Right, let me start again, because I'm getting myself in a knot here. It's, right, velocity is meters per second. So it's going to be distance. It's the beauty of doing a video, you can edit the bits out. So that's definitely going to be an edit. So you've got distance times the time to a minus 1. Let's put that in there. Okay. So that definitely don't belong in there. So that part there represents this bit.
Right.
Because it's one formula, they're put together like that, one part of the formula. And it's squared. And then there's your normal rules of arithmetic and algebra that apply, or laws of indices in this case. I have to multiply that into both terms, so it's going to go into this and this. But we're not there yet. That's your left-hand side. That's my E, finally. Now on the right-hand side, I've got half, which we don't care about. It's a constant, it's a number. It's actually a coefficient, so it doesn't count. We've got mass again. And then we've got velocity squared again, so we've got the same. Okay, so if I do a bit of tidying up, that would become L squared and T minus 2. We don't need to go this far because we can see immediately it's balanced. And that would do the same thing. Okay, so what's on the left is also on the right. So it's balanced. So we've got an m on the left, we've got an m on the right, we've got an L squared on the left, an L squared on the right. We've got a T to the minus 2 on the left and on the right. So it's balanced. So that'd be a straightforward yes. So the kind of thing Albert Einstein would have to do after he'd worked his formula out. Just check it like that. Okay? Let's do something that's a little bit more challenging.
What?
Yeah, I didn't think that one was that challenging because you can actually almost see that formula there is the same as that.
My eyes don't work same as yours.
In the sense of dimensions it is. Right, let's have a look further. We'll do a few of these, so we'll get them nailed down this morning. It'll be the first question on your assignment, it'll be the past part of your assignment this. Then we'll do deriving a formula, it'll be the merit part of the assignment. But it's not too bad when we get down to it. Let's do another one. We've been working away and we've worked out that force equals mvs. Okay? So that's S for displacement, by the way. It's not seconds, it's not a unit. It's a name in the formula, so it's displacement. So it's mass times velocity times displacement. So the amount of mass, the speed it's doing and how far it travels will give us force. So let's have a look. So force is ml t minus 2. It's actually mass times acceleration, that. F equals ma. Remember that formula. And then we've got mass. Then we've got velocity, which is lt minus 1. And then we've got displacement, which is length. Okay, so there I've got an m on the left and an m on the right, so that's correct. Then I've got one L on the left, but I've got 2 on the right. So it's going to be wrong. So one of these is wrong. That one's okay, I'm happy with that one, but that one's wrong. And then I've got t minus 2, and it's only got t minus 1 there.
So it's wrong as well.
So that's wrong as well, yeah. So it's wrong. Okay? So I was able to, I worked out my formula, I thought I got it sussed. And then when I check it, it isn't, so it's wrong. Okay? These notes are on Moodle, by the way. Probably not as in as much detail as I've got because I keep adding little notes on. It's certainly got the background to it. Another one. If I start moving things off too soon, just shout at me to wait. So another one, for example, is time taken for an object to fall a distance s. So time taken is square root of 2 times s over the acceleration, which could be gravity, of course. Gravity is acceleration. So I've got on my left here, I've got t for time. So this doesn't look like it's going to balance out, does it, at all? To look at this, because you've got one single term dimension on the left, and you've got a lot more on the right. So what have I got? I've got, this is a Another way of doing this square root is to the power of a half. You all remember that? So that can be written as a power of a half. So I could write like this actually. That's equally correct, which is good because that's what I'm going to do. So the 2 doesn't count because that's a coefficient out front, some constant, so we can ignore that. So we've got S is displacement, so we've got L. This is all to the power of a half. Probably need a longer bracket there. Divided by, I'm going to write this in a column, I'll explain in a second. So I've got acceleration. Acceleration is length over time squared. Extending bracket. And it's all square rooted. So this bit here is, because acceleration is the length, it's that really, and that obviously is the same as that dividing by it. Okay. The hardest bit of this is the laws of indices, I think. So that's that. So I can rewrite that, because this is a double inversion, I can bring this to the top. So I'll get inside my brackets. L, I can bring this T to the top. And L there. And this is all to the power of a half. Now you might start to recognise now this is getting, maybe not, but this is getting somewhere towards balancing, because the 2 immediately, the L is divided by L, so that's going to cancel to 1. So that's gone.
And it's like T squared.
And that's it. Then we've got left with T squared to the power of a half. So that's going to be, if I multiply that in as in laws of indices, it's going to be 2 over 2, so it's going to be 1. So it's going to be T1. So that goes with that. So I've got T on the left and T on the right, so it balances. Even though it didn't look like it was going to do that at the start, it does in the end. That's the thing with formulas.
What did you do with the half in the end, Kevin?
Sorry?
What did you do?
Right, the half is to the power of a half, because that's your square root.
Yeah.
So basically, if you've got your laws of indices say that you multiply that in. If it was just 2, that'd become 4. Nice and straightforward.
Okay,
Because it's going to be 2 over 2.
yeah.
Like that, which is equal to 1. That's what happened. Okay. I hope it's starting to make a bit more sense now for you. Not seem as scary. we'll do a few examples. I've got plenty here.
I've just got a question, because
Yeah.
we've got that 2s by the acceleration. Doesn't we supposed to change the acceleration to LT2 minus square on the bottom of it?
Yes. Indeed. What you're saying is it'd be this, wouldn't it?
Instead of t square.
But that means.
Instead of yeah.
Yeah, but that means the same as this. 'Cause that's what the minus.
Oh, so that's where it changed.
Yeah.
Right. Okay.
So I maybe missed a step out, but it was so that I could make it easier to rearrange to get that T to the top.
Yeah. Okay. Fair enough.
Just leave out the L. Okay with that? Like that. Right, so. Okay, to rub it all out. I've got what you want. May I suggest that if this seems difficult, it's only because it's brand new concepts, never come across. I was actually, this shows how sad I am. The other week I downloaded a book. Have you heard of Clerk Maxwell, James Clerk Maxwell? It's a shame hardly anybody's heard of him. He's one of Einstein's favourite scientists. Okay, he rates him up there with Isaac Newton, and he's the one that did. He made a lot of equations that then Einstein took and used. So it was Maxwell that showed through equations that the speed of light was a constant. So he showed that in these equations. And this is one of the things that, that Albert Einstein was thinking about, that made him think about this, how, because light is constant, then other things have to change in the formulas. I'm not going to go off at this tangent. But anyway, going back to Maxwell, he wrote a book. His famous book was called a treatise, because that's the kind of name they used in those names in those days. A treatise on magnetism, on electricity and magnetism, and it's a famous book. So all scientists have read it. You know, physicists or mad on physics will have read it, or certainly big portions of it, like they will have done with bits of Albert Einstein's and Isaac Newton. He starts his book off by talking about dimensional analysis. So it's like a textbook about dimensional analysis, the first chapter. That's what it's about. I've not read the book, though. I would like to, but you don't have time. But so it's a big book. I don't think it gets really down to his famous formulas to way into the book, but he starts with dimensional analysis. So it's like he's teaching a class really, and he's saying this is what you have to understand first. So he starts with this. So that shows, you know, to physicists how important this is. And we probably never, I suspect none of you have ever heard of it. I'd never heard of it until 2 years ago when I got given the job of teaching it. So I mean, it's amazing that something as important as this is unknown to us, really. But if you're doing physics, you have to be able to do it. Okay, so another example. One you probably recognise. A t squared. So this is your formula. S for displacement again, so distance moved. U is initial velocity. You remember this? You probably recognise this form, you've probably done this at some time in the past maybe. Yeah, it's one of the 4 laws of motion, equations of motion shall I say, for working out how far, there's 4 of them and they all will tell you how, depending which bits of information you've got, will tell you how far you've travelled or what speed you're doing or what the acceleration is, etc. And this is one of them. So this is your initial velocity times time plus the acceleration. Acceleration times squared times a half. Add them together and it gives you how far you've travelled. So if you know what your initial velocity is, which is often 0, so that's quite easy. So if you're in your car, initial velocity is 0, you often times 0. So you're not doing anything. And you accelerate, if you need to know what your acceleration is. So if you know that, and you know how many seconds you've been doing it for, you can work out how far you've travelled. And there's other ones that will tell you what speed you're doing in that time. And calculus is another means of doing all this, of course. Probably easier. But anyway, so does that balance? Again, it looks like it won't balance because there's so little on the left and so much on the right. You think that can't possibly balance. It's the beauty of these equations. They look so like they won't balance, but they do. Oh well, we'll see if it does. If it doesn't, we've got a problem because I've been using this for hundreds of years now. So let's have a look. So on the left, displacement is distance. On the right, so we've got a velocity, initial velocity, so it's just a velocity. So that's going to be our LT minus 1 plus. One thing I didn't say, when you're adding 2 things together, so if you've got L plus L, you would end up with 2L.
2L, yeah.
And that's just a number. So that would actually, in that situation, only count as 1L. Okay? It doesn't come into this, but I'm just mentioning, well, it will come into this a bit, but I'm just mentioning that bit of information. So, then we've got a half we don't need. Then we've got acceleration, so that's LT minus 2. And then we've got T squared, put that inside. Got to be careful when you put them inside and outside. If I put this minus 1 outside here, then I'd have to multiply it, multiply it into both terms. So it would be wrong. So you've got to have it inside in this case. When we did that one earlier with the velocity, speed of light, it was outside. then it multiplied into both terms. Right, let's have a look. So, basically it's a case of cancelling on the right hand side. So we've got here, so if I multiply this into this, these t's are going to cancel out there. Just me double check myself here. Ah, okay, yeah. That's right, let me just have a look at my notes. There's something going a bit iffy here. Oh, yeah, it's fine. It's fine. Ah, yeah, I know what I've done wrong, sorry. I'm looking at this and I'm going, I've got too many, I'm immediately spotting I've got too many t's here. One's not going to cancel, I'll miss this one out. That's why. So, human error. So, in there, if you'll bear with me being scruffy, I've got another t. Okay? That's why I had that panic attack, it didn't work. I just proved something wrong. Okay.
So would it be LT minus 1t?
Yes, yes.
Yeah.
Because this LT minus 1 is for the velocity,
Yeah, and then.
and this t is for this time, the one I forgot, foolishly. So now, if I look at this, this multiplies this, so these t's are going to go. Because it's minus 2 times the 2. Well, another way of looking at it is, your laws of indices, you subtract it, don't you, when you multiply them, or you add them, add in a minus, so they cancel out. Or you can look at it like that, which is, cancels out, same thing. Okay, with that hope. And then, I've got a t minus 1 times t, so same thing again, they're going to cancel for the same, exactly the same reason. So I've now got L plus L. Now you see why I told you what I just told you a minute ago, that is 2L. And the number out front don't count. So I've got, it balances.
So the number don't count at all? It's
No,
just-
no. Constants, numbers, these things don't count. So pi don't count, for example.
Okay.